Okay, Math 157ers, we are going to talk today about the t-distribution and hypothesis testing. And the t-distribution comes into play when the population standard deviation is unknown. And this is a much more legitimate hypothesis test, because when you're doing a hypothesis test, if you knew the population standard deviation, you would also know the population mean, and there would be no reason to do a hypothesis test or a confidence interval. So these two concepts of confidence intervals and hypothesis tests are actually relatively closely related. So our objective is to test the hypotheses about a population mean with sigma unknown. So to test hypotheses, we're going to use the t-distribution rather than the z. In terms of calculating our test statistic, the only thing different is that we replace our sigma with our f, and this follows that student's t-distribution with n-1 degrees of freedom. Big thing about the t-distribution is that critical value will change depending on the degrees of freedom. The t-distribution is centered at 0 and it's symmetric about 0. The area under the curve is 1. And so the area to the right of 0 equals the area to the left of 0, and those are both 1/2. Now as t gets bigger, the graph approaches but never equals 0. That's just like with the z-distribution. And here's my badly drawn picture from my previous attempt to record this. But the areas and the tails of the t-distribution is a little bit greater. So let's say that's your normal distribution, and that is badly drawn. If you were to draw the t, you probably see something like this. But just the whole point is that the area and the tails is greater. And the reason that's true is, if you're using S as an estimate of sigma, there's going to be more variability in the t statistic. Now, one interesting thing, as the sample size increases, the density curve of t gets closer to the standard normal density curve. So with a very large sample, if n is 1,000, let's say, you're going to find that your critical value for t is going to be almost the exact same as the critical value for z, and that your curves are going to look very similar. And that's by the law of large numbers. So let's test hypotheses about a population mean with sigma unknown. Here are some things that have to be true. The sample is obtained using simple random sampling, so they may throw that into a problem. You want to make sure that you've done that. The sample has no outliers, and the population from which the sample is drawn is normally distributed, or the sample size is larger than 30. Okay, so they're going to need to say, or you're going to have to make sure that the population from which that sample is drawn is normally distributed, or they're going to have to give you a sample size of greater than or equal to 30. So these are what hypothesis tests look like. You have a two-tailed test where you're testing H naught mu equals mu naught, and then H1 mu is not equal to mu naught. You have a left-tailed test where the mean is greater than or equal to the test statistic. And then you can have a right-tailed test where the test statistic is greater than the mean. Oops, I did that backwards. Where here's where the H1 is where they're not equal. H in left-tailed test, mu is your test statistic is less than the population statistic, and and at H1, your right-tailed test is that your test value of mu is going to be greater than the population mean. Okay, so we always have to select the level of significance based on how serious we are about making a type 1 error. So your level of significance could be 0.01, 0.05, 0.1, 0.01, and so on. So the first thing you would do is compute this test statistic. I want you to see this test statistic, but I want you to use technology to actually compute it for you. I'm going to show you how to do that in a minute. And then you would use table 6. That's the old-fashioned way of to determine the critical value, but we are going to use StatCrunch and the t-calculator to find the critical value. So in a two-tailed test, the critical region is below negative t of alpha over 2 and above of t of alpha over 2. And the reason why we need to use alpha over 2, so if I was testing at like the 0.01, well, you know, 0.01, in each tail there needs to be half of that. So 0.01 divided by 2 is going to be 0.005. So the area in this tail is 0.005, and the area in this tail is 0.005. So if your calculated t falls into either of these areas, the question is, what would we do? Okay, and that area is the rejection region. And then here, negative t of alpha over 2. Why is that true? Well, if alpha, again, was 0.01, and there's our rejection region. And then right-tailed, there's your critical region, or your rejection region. Okay, so what this is just saying, if your test statistic, the one that you calculate, is in those critical regions, you reject the null hypothesis. So if your test statistic is in those shaded regions, you're going to reject the null hypothesis. So here they say use table 6, which we're not going to use, to estimate the p-value. Okay, on a two-tailed, that's how you would look it up. I go the wrong way. Okay, so just let's ignore this part of the lecture. I'm just going to kind of scroll through. So you have two approaches. You have a classical approach and a p-value approach. A p-value is just the area in both tails. So if you set the rejection to 0.01 and you came up with a p-value of if you're doing a two-tailed test, and your alpha is 0.01, but if the area in both of these tails is like 0.006, well, that's less than 0.1, so we would reject. And we're going to go step by step through a couple of problems, and then you state the conclusion. All right, let's look at this problem. Assume the resting metabolic rate of healthy males in complete silence is 5710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found their mean to be 5708.07 with a standard deviation of 99.2. Is there evidence concluding that the mean RMR of males is different? So different means a two-tailed test. So H0 is this number. H1 is our X bar value. And our sample standard deviation is 99.2.05. Our N was up here. Okay, and our alpha is 0.05. So that's all the information we need. So they're saying it's a two-tailed test. The sample size is large. All right, so that's what I wrote here. Now this is how they calculate the t statistic. And they got 0.013. But I'm going to show you a different way to calculate your t statistic. So let me close this stuff up. This is how I would prefer you to do it. Okay. Stat, t-statistic, one sample with summary, just like we did for confidence intervals. All right. The sample mean was 5708.7 right here. The sample standard deviation was 992.05, and the sample size was 45. And unlike in Chapter 9, we're going to do hypothesis test, where H naught is 5710. And we're doing a one-tailed, so not equal. Compute. Now let's look at all this good stuff we got here. They got negative 0.013. And we got not that. So what did I put in wrong? 50 sample mean. Let's see, 5708.07. Let's make sure. 992.05. I don't know why we're getting a different number. Oh, 0.07. Look what I did right here. 5708.07. There it is. So look at our t, negative 0.013, which is exactly what they got here. All right, let's go on. All right, since this is a two-tailed test, we determined the critical values at the alpha equals 0.01 level of significance. All right, so we need to find the area. We need to find the z-value that corresponds to an area of 0.025, because what we do in the two-tailed test is you take that and you divide it by 2, 0.025. And they got negative 2.021, but we're going to make it easier for us. So if you go to Stat, Calculators, T, we've done this before, the degrees of freedom are 44. And we need to find the z-value that corresponds to 0.025 area. Negative 2.015, and that's, I think that's what they got, negative 2.015, and my thing won't move, negative 2.02. Yeah, they rounded. What did they do? Negative 2.021. And that's the difference between the table and the in this calculator, which is actually more accurate. Regardless, our t-value is still going to be between that critical value. So if we draw, here's our critical values, negative 2.021. And positive 2.021. And because that the test statistic is right here, it's in between these two values, we fail to reject. It needs to be in those red shaded areas for us to reject the null hypothesis. Now, how can we do the p-value approach? Well, the p-value approach is actually much easier because we look at our alpha, and remember our alpha was 0.05, and StatCrunch actually, StatCrunch actually calculates a p-value for us. And what do they get for the p-value? They don't actually calculate it. Our p-value is 0.09896, which is greater than 0.05. So if our p-value is greater than our alpha, we fail to reject. And that's a very simple way of doing that. So how do we say? Our solution is that there's insufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean RMR of males listening to calm classical music differs from 5,710 kilojoules per day. All right. So let's go, and this is just another example, but let's work through a couple of problems. Let me close this and go to the study plan. And I want to go, oh, it might help if I was in the right section. All right, I'm going to look at 10.37. All right, we're going to test the hypothesis H0 that mu is equal to 100 versus H is not equal to 100. We have a simple random sample of size 23 obtained from a population that is known to be normally distributed. So all our conditions are met. For some reason, StatCrunch is not opening on there, so we have to open this calculator. I have another window up. So we're going to go stat T statistics, one sample with summary, because we have summary data. Sample mean is 104.9. Our sample standard deviation was 8.6, and our sample size was 23. We're going to test that it's equal to 100, and we're doing a two-tailed test, so not equal. Compute. Well, our T statistic is calculated for us, 2.732. Let's go with 2.733. All right, so if the researcher decides to test this hypothesis at the 0.01 level of significance, determine the critical values. Easy enough. Now, remember, because this is a two-tailed test, we had to take that critical value of 0.01 and divide that by 2. So the area in each tail is 0.005. Calculators, T. All right, degrees of freedom, remember that's equal to n minus 1, so 22. And then we're looking for 0.005. So on the low side, it's negative 2.818. And how many decimal places? 2.88. It wants 3 decimal places. So negative 2.819 is what we're going to use. Now remember, these are symmetric, so the other one should be 2.819, but we can check that by deleting this, going to the other side, and I know, so reference 0.005, then it gives you 2.819. All right, why does it not like our answers? Oh, look what I did here. I put a comma instead of the actual number in. Okay, well, it's a two-tailed test. The only one of these pictures that detects a two-tailed test is C. But will they reject? Well, 2.733 is not in the tails. So we're not going to reject the null, because if you look, negative 2.819 and 2.819, we're looking for 2.733, which is not in the tails. So there is not sufficient evidence for the researcher to reject the null, since the test statistic is between the critical values. There we go. All right, let's do this one because it's giving us a one-tailed test. So at first we have H0 mu is equal to 20, H1 mu is less than 20. Left-tailed test, simple random sample of 18, obtained from a population that is known to be normally distributed. Okay, so we need to compute our t-statistic. Do I still have that up yet? And if you come in here and you go options, edit, you can go and just not have to restart. Sample mean is 18.1. Sample standard deviation is 4.4, and our sample size is 18. The hypothesis test for it's equal to 20, and the left tail test for it less than or equal to 20. Let's hit compute. There's our t-statistic, negative 1.832. All right, left-tailed test. We need to find this left-tailed region. All right, now part of the problem with using the tables is that you can't get, sometimes it's hard to get a proper p-value. However, we already calculated our p-value. Our p-value is known to be 0.0423. So which one gives us it between where does 0.0423 lie? Doesn't lie in A. 0.025 to 0.05, yep, it lies in here. It lies in B. All right. Now remember we talked about p-value. Our alpha is equal to, we're testing at t-distribution. Where does it tell us our alpha? Huh. I don't see anywhere on here where it gives us, oh, I can't even read. If it's at the 0.05 level of significance, well, let's go back. Our alpha was 0.0423, and if your p-value is less than your level of significance, you will reject the null. There we go. So that's a p-value approach. There was one more question I wanted to do where you actually had the data. All right, the mean waiting time at the drive-thru of a fast food restaurant from the time an order is placed to the time an order is received is 86.7 seconds. So H0, right away, we know is going to be mu is equal to 86.7. And it's always very good to write down let's go back to the problem. Manager devises a new drive-through system that she believes will decrease wait time. So we're testing it against the alternative, which is okay. So we've written out our hypotheses, and it's going to be a left-tailed test here. So if we knew, so this is the side of the test. All right. As a test, she initiates the new system at her restaurant and measures the wait time for 10 randomly selected orders, so our n is equal to 10. The wait times are provided in this table. Because sample size is small, the manager must verify that the wait time is normally distributed and the sample does not contain any outliers. So here, it looks good. You see there's no real outliers, and if you look, it's within these two curved lines, so it is. So the conditions are satisfied. Oops, go ahead and continue. All right. Is the new system effective? Use alpha equals 0.1. So what we can do, we can use a p-value test. We're going to try to open this data in StatCrunch, which I think it should let me do. Okay. Data, excuse me, stat, t statistics, one sample with data. It's in variable 1. H naught is at the mean, 86.7, and the alternative is that it's less than 86.7. That's all you have to write. So you select your column, choose your hypothesis test, put in the conditions, compute. Well, our p-value ends up being 0.0649. So let's see what they're asking us. All right, so at the alpha equals 0.1, so, and our p-value is 0.0649. If we look at this, this is less than that. So at the 0.1 level of significance, we would reject the null. No. Yes, we would reject the null. So it does fall into the critical region. So there's sufficient evidence to conclude that the new system is effective. Because if our p-value fell into this critical region, which is this blue-shaped area, because remember, this area is 0.1, and the area that we found was 0.0649, and that's less. The test statistic does fall into the critical region, so there is sufficient evidence to believe the new system is effective. Fingers crossed. All right. Okay, so that should give you a taste of everything you're doing here. So I'm looking at number 9. Golf solution requires that the golf balls have a diameter that is 1.68 inches. Determine if golf balls conform to the standards. A random sample of golf balls was selected. Diameters are shown in this table. Let's see. Yes. Well, that could be an outlier, but it still falls within these two curved lines. So I'm going to go with yes. Okay. So do the golf balls conform to the standards? Well, here again, this is a two-tailed test because it's just trying to make sure they're not too big or not too small. So you'd click to open the data, open it in StatCrunch. Our H naught is mu equals 1.68, and our alternative is that it's not equal to 1.68. Stat T statistics, one sample with data. So that's my column. H naught is 1.68. We're doing a two-tailed test. Compute. Our p-value was 0.44. We're using alpha equals 0.05. It would only reject the null if our p-value is greater than 0.05. So the null hypothesis was that they equaled 1.68, so that they were conforming. So there's not sufficient evidence to conclude that the golf balls don't conform. Okay, so hopefully I've given you enough to get you going. Actually, let's look at number 9, because number 9 is talking about bringing in a confidence interval. Several years ago, the reported mean age of an inmate on death row was 44.6 years. Sociologists wondered whether or not the mean age of death row inmate has changed. She randomly selected 38 death row inmates and find their mean age is 40.2. So our N is 38. Our X bar is 40.2. And write this down with me. Our sample standard deviation is 10.9. And our thing that we're testing is 44.6 years. And we're trying to figure out whether or not the mean age has changed. So what do you guys think? One-tailed, two-tailed? Well, let's write it out. H naught is that the mean equals 40.2. And the alternative, she just wants to know if it's changed. So she wants, it doesn't matter if it's bigger or smaller. The alternative is that U is not equal to 40.2. And all the other things that we know, N is 38, X bar, oops, did I write that down? Oh, 44.6, oops, see that's why it's always good to check your work. It's actually mean equals 44.6. And then we also want to find out that it's not equal to 44.6. Our X bar value was 40.2. And our sample standard deviation is 10.9. And we're checking at the alpha equals 0.1 level. All right, let's close all this up. So stat, t-statistic, one sample with summary. Sample mean is 40.2. Sample standard deviation was 10.9. My sample size is 38, which means we have 37 degrees of freedom. H naught, where that is 40.2. And we're just doing the not equals. Compute. So my p-value was 1. Oh man, that's a big p-value. And that makes sense because our sample standard deviation was 10. I'm going to double check that because that's so big. Yeah. Do you believe the mean age has changed? Well, if p-value is greater than alpha, we fail to reject. And if you look, what's our t? What was our t value? Our t statistic was 0. Let me just double check my work. That's such a wacky number. Oh, here's what I forgot. Look what I did wrong. 44.6. See, sometimes when things don't look right, I gotta redo it. All right, our p-value is 0.0175. That makes a lot more sense to me. And our t-statistic is negative 2.48. So we're testing at the 0.01 level. Well, our p-value is less than 0.1. So we're going to reject, and it also means that that test statistics is in the critical region. So test statistic falls in the critical region, and we're going to reject the null. We don't even need to calculate we need to go to the T calculator and do that calculation. All right, construct a 90% confidence interval about the mean age. Well, the reason I wanted to do this problem was just to kind of show you how easy it is to change. Well, we're just going to change the confidence level of 90, because all this stuff is the same. And our confidence level is 37.2, 43.2. All right, let's continue. What does the interval imply? Well, look, our given mean age is 44.6, which is not in our 90% confidence interval. So since the mean age is not in the interval, we would reject the null hypothesis. So you can also do these by confidence intervals, come up with your 0.1 level of significance corresponds to a 90% confidence interval. Because remember, 1 minus 0.1 gives you 0.9, which is a 90% confidence interval. So since the mean age is not in the interval, reject the null. Okay, I think I have shown you enough stuff to get you started. So good luck with section 10.3, and let me know if you have any questions. Thanks.